Hello class, we want to continue with our studies on chapter 8. Properties and electron configuration. Valence electrons determine chemical and physical properties. Therefore, elements in the same column have similar properties. Because the elements in the same column have the same valence electron. Noble gas electron configuration. The noble gases have 8 valence electrons, except for helium, which has only 2 electrons. So noble gases are non-reactive. The noble gases are so non-reactive because their electron configuration of the noble gases are filled, so they are stable. The subshells of noble gases have filled electron configuration. It makes them very, very stable, so they don't react. Everyone wants to be like a noble gas. Alkali metals, group 1 metals, have 1 valence electron. In their reaction, the alkali metals tend to lose their valence electron, resulting in the same electron configuration as the noble gas. And when they do that, they form a cation with a +1 charge. Or because they want to have filled electron configuration, just like the noble gas before them. Because the noble gas before them are not reactive. Because their subshell electron configuration is filled, or because they have filled electron configuration. Halogens have 7 valence electrons. In their reaction with metals, the halogens tend to gain an electron and attain an electron configuration of the next noble gas, forming anion with a plus and -1 charge. So in their reaction with nonmetals, they tend to share electrons with the other nonmetals so that each can attain electron configuration of that of a noble gas. So for halogens, with metals that can give them electrons, they pick it up. And when they have a noble gas electronic configuration, they're okay, they stop. They now interact electrostatically with the metal, which has a cation. But if they have to react with a non-metal that cannot give electrons, they can share. They share. Each of the non-metals share in order to have the noble gas configuration. Let's look at trends in periodic table. Effective nuclear charge. We'll look at trends in effective nuclear charge. We'll look at trends in atomic size. We'll look at trends in ionic size. We'll look at trends in ionization energy, electron affinity, electronegativity, and metallic character. How all these affect the property of elements. That's why we are looking at them. How these trends affect the way these elements react or behave. That's why we are going to look at all these trends. Shielding. In a multi-electron system, electrons are simultaneously attracted to the nucleus and repelled by each other. Outer electrons are shielded from the nucleus by core electrons. Because of this shielding, the outer electrons do not experience the full strength of the nuclear charge. The core electrons shield the outer electrons from the positive attractive force of the protons in the nucleus. So the outer electrons really don't feel the full strength of the positive charge. So the effective nuclear charge, the net positive charge felt by a particular electron is Z minus S. Z is the nuclear charge. S is the shield due to electrons in lower energy levels. And the trend is that S electrons shield more than P electrons, and P electrons shield more than D electrons, and D electrons shield more than F electrons. So the effective nuclear charge is Z minus S. So screening an effective nuclear charge. Screening an effective nuclear charge. We'll look at that. So let's take this nucleus. It has a +3 charge. Then it has a core electron, 1 s2 electrons. This is lithium. Then this is its valence electron. So its effective nuclear charge, the effective nuclear charge that this electron feels is +3 minus 2, which is +1, not the +3. Let's look at trends in atomic radius or the main group elements. Atomic radius increases down the group. The valence shell further from the nucleus, an effective nuclear charge drops. So the atomic radius increases down the group. That's true. So the valence electrons are further away from the nucleus. And this affects the effective nuclear charge, which drops as you go down the group. Atomic radius. Atomic radius decreases across the period, left to right. Electrons added to the same valence shell. So the effective nuclear charge increases across the period. So atomic radius decreases across the period from left to right of the periodic table. Electrons are added to the same valence shell, that's the reason. So the effective nuclear charge increases across the period from left to right. So let's take, for example, choose the larger atom in each pair. So we have carbon. This is carbon. And this is oxygen. And we say the atomic radius decreases from left to right. Atomic radius. Decreases. So with that, we know that carbon is larger than oxygen. Let's look at lithium and potassium. Down the group, atomic radius increases down the group. So lithium is larger than, is smaller than potassium because potassium is further down the column. Carbon or aluminum? Where's carbon? This is carbon. This is aluminum. You see them? They should be almost the same. You see they're diagonal. Smaller. This is smaller. Oh no, I'm sure aluminum is larger. Aluminum should be larger. Yeah, aluminum should be larger. So let's look at that. Carbon is further left in the periodic table. Potassium is further down in the column. Carbon, aluminum is further left and down, so aluminum is larger. Let's look at trends. Trends in atomic radius for transition element. Increase in size down the group. The atomic radius of transition metals are roughly the same size across the D block. All transition metals have the same valence electrons, shares across a particular period. So valence shell NS2, not the D electrons. Effective nuclear charge on the NS electron approximately the same. So the size of transition metals is approximately the same. Let's look at trends in ionic radius. Ionic size increases down the group. Cations are smaller than neutral atoms. Anions are bigger than neutral atoms. Cations are smaller than anions. Larger positive charge, smaller cations. So isoelectronic species, aluminium less than magnesium, have 10 electrons each. Larger negative charge equals to larger anion. So oxygen 2- is greater than fluorine-, has 10 electrons each. So that's trends in the ionic radius. Please try and study them so that you can know them. So we can see some patterns here for atomic radius. You see the main group elements, group 1A, 2A, 3A, 4A, 5A, 6A, and 7A. So these are their charges. Hydrogen can have +1 or -1. It's equals. Then all group 1 has a charge of +1. All group 2A has a charge of +2. Because those are their valence electrons. Then group 3 +3, group 4 -4. Then here you can have a +4 and 2+. Group 5 -3, group 6 -2, group 7 -1. So you can see their sizes. So you see, the ionic radii for cation increases down the group. Look at it. Just look at the sizes. Increases down the group and decreases from left to right. Yes, decreases down the group and increases from left to right, or decreases from right to left. Cations also increase down the group, and decreases from left to right. Increases, yeah, increases from left to right. It's increasing. So choose the larger of the pair. So choose the larger of this pair. Let's look at it. S minus is larger because there are more electrons, 18 electrons, for the 16 protons to hold. The anion is larger than the neutral atom. Calcium is larger because its valence shell electrons have lost 2 electrons to form calcium 2+. The cation is always smaller than the neutral atom. Bromide is larger because it has fewer protons, 35 protons, to hold 36 electrons than those of krypton. For isoelectronic species, the more negative the charge, the larger the atom or ion. Please try and do some practice. Take your time. Do practice. It will help you understand this better. So try and do this practice. Order the following set by size, smallest to largest. So please do this practice at your spare time. Now we want to look at ionization energy. Minimum energy needed to remove an electron from an atom in the gaseous state. This process is endothermic. Valence electrons easiest to remove, less ionization energy. So the first ionization energy equals the energy to remove the first electron from a neutral atom. So for example, we have let's say this is an atom. We need this first energy to remove this one electron. So second ionization energy is the energy to remove electron from a +1 cation. So you have the cation, you put the second ionization energy to remove the second electron. Let's look at trends in ionization energy. The larger the effective nuclide charge on the electron, the more energy it takes to remove it. The further the electron is from the nucleus, the less energy it takes to remove it. So first, ionization energy increases across the period because the effective nuclear charge increases. But it decreases down the group. The valence electrons are further from the nucleus. So let's see how this plays out in a chart, in a table. So you see, this is helium, and this is hydrogen. You see the first electronic ionization is very high. Then let's look at lithium. Lithium to neon, these are periods. Lithium has very low ionization energy compared to neon. Then look at sodium, you see. And we look at potassium. Those are the periods. So this is period 1, period 2, period 3, period 4, period 5. But if you look at ionization energy is decreasing down the group. Look at alkali metals, decreasing down the group. So that is the first ionization energy. So choose the atom in each pair with the highest ionization energy. So this is magnesium, and this is phosphorus. Because ionization energy increases across the period from left to right, magnesium has less ionization energy. Phosphorus has the highest ionization energy. Let's look at gold and copper. Copper, this is copper. I mean silver and copper, this is silver, this is copper. I mean this is copper, this is silver. You see they're in the same group. But silver is lower than copper. So silver is going to have less ionization energy. Copper will have a higher ionization energy than silver. Let's look at calcium and rubidium. This is calcium. And where is rubidium? This is rubidium. I'm sure calcium will have a higher ionization energy than rubidium. So those are some trends. So that's phosphorus, that's copper, and that's calcium. Irregularities in trends. Let's look at some irregularities in trends. Ionization energy generally increases from left to right across the period, except from 2A to 3A or 5A to 6A. There's a reason for that. So let's look at 2A. This is 2A. And this is 3A. Let's see. What am I doing? Let's see what is on here. No, let's look at it. Beryllium. Beryllium is in group 2A. Okay, this is 2A. And boron is in 3A. You see, the subshells in beryllium are filled. But boron, there's one electron in the p subshell. So the ionization energy of beryllium is higher because it is more stable than that of boron. That's what I mean by 2A to 3A. That's the example. Which is easier to remove, an electron from boron or from beryllium? Why? That from boron is easiest. You see, it's not paired alone. But here they are paired, they are stable. So now we want to look at 5A and 6A. 5A and 6A. So this is 5A and this is 6A. Let's look at their orbital diagram. Which do you think is more stable? Of course, 5A. Because it has half field. This is more stable than 6A. You see, there is pairing. This is more unstable than this. So this will have a higher ionization energy than this. So let's look at trends in successive ionization energy. successive electron costs more energy due to successive increase in effective nuclear charge. Regular increase in energy for each successive valence electrons, so greater increase for core electrons. So it's more costly to remove an electron after an electron has been removed from an atom. So we can see that first ionization energies for sodium. Look at the second ionization energy. It's much more costly. Magnesium, first ionization energy. Look at the second ionization energy. And look at the third. Aluminum, you see the first three, but look at the fourth. Because you are entering into the core electrons, it becomes much more expensive. The next term we want to look at is electron affinity. Energy released when a neutral atom gains an electron in the gas state. So the equation is like this. You form an anion, defined as exothermic, but may actually be endothermic. Some alkali earth metals and all noble gases are endothermic. Why? Because they don't want electrons. They don't want to accept electrons. They prefer to give electrons out because that will make them have the noble gas character. The more energy that is released, the larger the electron affinity of the atom. The more negative the number, the larger the electron affinity. Let's look at trends in electron affinity. Generally, electron affinity increases across the period, becomes more negative from left to right. Highest electron affinity in period is from the halogens. Group 5A generally have lower electron affinity than expected because of extra electron mass pair. Group 2A and 8A generally have very low electron affinity because added electron goes into higher energy level. They don't want it. So those are some trends of electron affinity. So you see, this one's group 1, group 2, much more smaller. Then group 3A, negative. So you see, look at the trends down the group and across the period. This has the highest. It loves it. Loves electrons. They love electrons. They love electrons. For noble gas even is greater than 0, positive. They don't want to give electrons. They don't want to add electrons or remove electrons. Electronegativity. The ability of an atom to attract electron towards itself in a chemical bond increased across the period from left to right. Fluorine is the most electronegative element. Decreases down the group, top to bottom. The larger the difference in electronegativity, the more polar the bond. We want to talk about metallic character. Metallic character. Is how closely an element's properties match the ideal property of a metal. More malleable and ductile, but better conductors, and easier to ionize. Metallic character decreases from left to right. Metallic character decreases from left to right across the periodic table. Metals are found at the left of the periodic table and non-metals at the right of the periodic table. Metallic character increases down the column. Non-metals are found at the top of the middle main group elements, and metals are found at the bottom. So let's look at the metallic character. So metallic character increases down the group. But it decreases across the period. Metallic character decreases across the period, but increases down the group. So magnesium and aluminum. What's magnesium? This is magnesium, and this is aluminum. Which one has a higher metallic character? Of course, it's magnesium. Let's look at silicon and tin. This is silicon, and this is tin. Of course, tin has a higher metallic character than silicon because metallic character increases down the group. Let's look at bromine and toluene. This is toluene. And where is bromine? This is bromine. Of course, toluene has higher metallic character than bromine. So I want to thank you again. We've come to the end of chapter 8. Thank you so much.